All right, so I've got an offer for you. Right now, today, I will give you $1 million. It's yours. It's all yours. That's my offer. Or I'll give you 1 cent. Then after a day, I'll give you 2 cents. Then after another day, I'll give you 4 cents. Then after another day, I'll give you 8. So after 1 day, after 2 days, after 3 days, and I'll continue that for a whole month. Which option do you choose? Make your decision now. $1 million, straight up cash. Or I'll give you a penny, and then 2 pennies, then 4 pennies, then 8 pennies for a month. So which one did you choose? Did you choose the right one? Let's take a look and see. In order to see what's going on here, basically what you have to know is what is really happening over here with this guy. And so I'm going to kind of simplify it down to day number 1. Now you have 2 pennies. Let's go back. Day number 0, you started with 1 penny. After 1 day, I gave you 2 pennies. After 2 days, I gave you 4. After 3 days, I gave you 8. 4 days would be 16. So what is happening every single time over here? Hopefully, you said it's doubling every single time over here. The number of pennies is doubling every single day that I give you. But let's look at what mathematically is happening. From day 0 to day 1, notice it multiplied by 2. You took your original penny times 2. Then, on day 2, you took your original penny times 2 times another 2. Then you took your original penny times 2 times another 2 times 2 again. Then you took your original penny times 2 times 2 times 2 times 2 again. Do you notice a pattern here? How many 2's are right here? There's 1 2. How many 2's are right here? There's 2 2's. How many 2's are right here? There's 3 of them. And how many 2's right here? Hopefully you recognize the pattern now. There's 4 of them. So what you are doing is, to get your Y value, you are taking the original penny and you're multiplying it times 2 raised to the x power. This is the new type of function that we are looking at in this chapter. In case you don't know, this is called an exponential function. An exponential function is when you are increasing by not the same amount every time over here, but you're increasing by the same factor every time. It's doubling every time. In the real world, we say that we are increasing by the same percentage every single time. Notice every single day, you are gaining 100% of what you had the day before. Meaning from day 1, or day 0 to day 1, you had 1 the first day, but then you had 2. You gained a whole penny 100% of what you had before. From day 1 to day 2, you got 2 to 4, meaning you gained 100% of what you had before. Meaning on day 2, or day 1, I should say, you had 2 cents. You gained another whole 2 cents to get to 0.04 cents. And then to 0.04, you added 100% of what you had before to get to 0.08. So you are gaining 100% every single day. That is what we call an exponential function. Now we're going to get into a little bit more detail of that exponential function over the next few slides and the next few minutes that we go through this. We're going to kind of break this into several sections here where we talk about some real world context for exponential functions. Then we talk about the graphs of exponential functions, and then we come back again to a little bit more real world context with some very specific types of exponential functions, very specific situations that you can see. But I first want to help you out here. Let me go ahead and tell you. Option number 2 is better. Let me show you why. The true equation would be 1 cent, or 0.01, times 2 raised to the x power, where x is the number of days that I am doing this for you, which would be a whole month. So let's go to our calculator. Let me show you why option number 2 is actually better. Option number 2, you take 1 cent and you multiply that 2 to 31st power, because it's going to be 31 days or 30 days if you use April. And Mr. Harrison is going to end up on that very last day paying you $21,474,836. That's just the last day. That doesn't count the day before. If you think about this, on day 30, I would be paying you $10,737,418.24. So if you chose option number 1, I'm sorry, you missed out. And it's because you didn't understand yet how exponential growth, what we call this, helps me describe how this money, even though I only started a penny on day 0, can grow into a large amount of money by the end. So this type of function, exponential growth, and we're going to also talk about exponential decay, describes when something grows by a percentage or decreases by a percentage, growth or decay. If you did your math in the real world assignment, you should have found, it's very readily available on the internet, you should have looked it up and said, what kind of math function represents the coronavirus spread? You would have seen an exponential function. This is the total cases in the world for the coronavirus. And you can see that it follows this pattern very slowly at first, but then it jumps up really quickly. Just like what we noticed with our money, if we were doing 1 cent the first day, 2 cents the second, 4 cents, 8, but then it jumps up to $21 million. So this is exponential growth. Exponential growth is when something increases by a percentage. Now we will come back to that example of the real world, the coronavirus, a little bit later, because I want to teach you how to actually find that equation later on. First, I'm going to give you the basic idea of what the equation looks like. I'm sorry, you guys know I'm using an old saved file here. This is 6-1 and 6-2 in your textbook, Exponential Growth and Decay. So exponential growth occurs when you have a quantity increasing by the same percent in each unit of time. It doesn't necessarily have to be time that we're talking about exponential growth, but typically we do. In your textbook, I'm going to warn you ahead of time, your textbook is going to have y equals a times b to the x. Or they may put that b in parentheses, kind of like this 1 plus r is in parentheses. But both of these functions essentially mean the same thing. The c, or the a, is the initial amount. It's the beginning amount. If you'll notice over here, what we figured out is every single time I was multiplying that original penny, the 1 cent that we started with, the beginning amount. The t is the time period, the number of times that I multiply. In our example with the bank account, we were talking about the day here that Mr. Harrison doubled that money every single day. So the x was our day. So typically, yes, instead of t here, you may also see x. Then the 1 plus r is called the growth factor. Like I said, it was multiplying by the same factor over and over again. It was doubling every day. That is why I knew, and we're going to learn this as we go through this chapter a little bit more in detail as we go. I knew the growth rate, the r, was 100%, because 1 plus 1 would be 2. That would be r would have to be 1. Now here's the tricky part. The growth rate typically is going to be given to us as a percentage in real world terms. We have to make sure that we change that percentage to a decimal. So that's why 100% was 1 right here. So if we go back to our example that we just looked at, our beginning amount was 1 cent or 1 penny. Our rate was 100%. We were doubling every single time. So 100% as a decimal, 100% as a decimal is 1.00. If you plug in 1.00 there, you would get 1.00 plus 1, which is 2. That's why it was doubling every single time. So here's the good news. If you can just remember that every time you see something doubling, it's 100%, or every time you see something growing by 100%, it's going to double, it'll make that portion there in the parentheses very easy for you. It's always going to be 2 there when you are doing 100%, or doubling is always going to be 100% growth. So what we have is we have the beginning amount, 1 plus the rate of growth, raised to the time, or raised to the x if it's a problem that you're dealing with x instead of t. The key thing there is realizing the reason this is called an exponential function is because the variable is in the exponent. That should hopefully ring a bell there that is not a polynomial. This does not follow the same type of pattern as a polynomial, and it doesn't do a lot of the same things that a polynomial does, even though we'll still use some of the skills that we've learned all year to help us when it comes to graphing and when it comes to things like solving. We'll still use those polynomial skills. But this is how exponential growth works. When something grows by a percentage over time. So let's look at another quick little example. And you're going to have a few of these on your homework, and you're going to have a few of these on your test. So let's come over here to an example of an exponential growth function dealing with a bank account. A bank account is a prime example of when you would use an exponential growth function in real life. You deposit $500 into an account that pays 8% annual interest compounded yearly. So first of all, let's get a couple things out of the way. Deposit $500. This is what you begin with, your starting amount, right? Pays 8% interest. That's the amount that it's adding every single year. And the reason I know it's every single year is because it says compounded yearly. We're going to come back to that word compounded a little bit later in this video. But compounded yearly means how many times the interest is added each year. Compounded yearly means once a year. So we're going to write a function that can be used to find out how much money you have. Stop there for a second. We're going to write the function first. Then we're going to answer the second part of the question. The reason I'm doing this is because I want you to be able to apply this not just to one problem, but to multiple problems. Not just to find one answer, but to be able to do this for multiple answers. So we're going to deposit $500. That's my beginning amount. So thinking back to what we had on the previous page, we said an exponential growth function has the beginning amount times 1 plus the rate raised to the time. Or, another way to say that is the beginning amount, A, times the B, which is the 1 plus R, same thing, raised to an X power. I don't care which format you use, either one basically means the same thing. A couple of you I saw when you were doing your math in the real world project assignment there, you had a little bit of funky looking things here where you had f of x and you had x sub 0 and things like that in there. It's not that that stuff is wrong. I'm just trying to simplify it down to a little bit easier things to remember for you. So, the beginning amount. What is the beginning amount? It's $500. So the amount in my bank account is going to be $500 times, well, what's going to be here? Well, it's going to be 1 plus the rate, or 1 plus 8%. But how do I do that? I do 1 plus, and then I put 8% as a decimal, 0.08. Be very, very careful with that number right there. 8% is not 0.8, it's 0.08. If you do 0.8, that would be 80%, which would be really good, but no bank account's going to do that. There's not many bank accounts out there that will do this. This would actually probably have to be more of an investment account. This would not be a normal savings account. Normal savings account have very low percentages of interest. And we'll talk about that real world context here just a little bit. So, we raise this to the t power, or if you want to put x there, you can put x there. Now, I know somebody's sitting there screaming in their computer, Mr. Harrison, you didn't put the 6 in. You're right, because I'm not trying to find the answer. This right here is the function that represents what's happening to my account for any number of years I would want. So now I can use this function to figure out multiple numbers of years. Or I could use this function to figure out the amount right here that I would have and figure out how many years it would take me to get there. That's going to be something we do a little bit later in the chapter, is we're going to look at the other way around. Instead of me giving you the years, I give you the amount and you find the number of years that it takes to get that amount. That's more maybe real world for some of you. How many years do you need to invest in something before you get the amount of money that you want? That's going to be something you want to know down the road. So now what we are going to do is, yes, we are going to use our function now. Now we are going to find the amount in the account after 6 years. So I can use either 1.08 raised to the 6th power, or I can use 1 plus 0.08. Either one is fine. I'm using this one just as a simpler version here because it's easier to type in the calculator. But now I take out my handy dandy calculator and I do 500 times 1.08 raised to the 6th power. Notice that's very similar to what you did for the pennies example that we started off with. So we raise it to the 6th power, we press enter, $793.44. Yes, you will lose points if you cannot round to the proper amount of cents. You do need to make sure that you can round to the hundredths place when you're dealing with money. So when you look at this, this is how much money I'll have in my account after 6 years. Now, that same concept there can be applied to a lot of life situations that grow by a percentage. Typically, bank accounts are a big one. Population is another one. We'll look at an example here in just a little bit of the bacteria population. It can happen in multiple different formats, different things that grow at a percentage rate. So here's the one thing I want to point out to you, and I'm going to probably do a little live WebEx with this to kind of drive this home a little bit more than just me giving you a lesson here on YouTube. But what you should know here is that you gain this money for interest. You gained it by doing nothing. You don't have to work for that extra $293.44 now that's in your bank account. But you do have to be patient. You cannot take the money out early. And it's important to understand, we're going to talk about it in particular, the shapes of these graphs. Think about that coronavirus shape. It starts off slow, but then it grows really, really fast near the end. That's how exponential growth works. And so we're going to look at that in a little bit more detail as we go through some of the other pages, as we go through and talk about the graphs in a little bit more detail. So let's do another example of exponential growth. A savings certificate of $1,000 pays 6.5% annual interest compounded yearly. Savings certificate is just basically the same idea as a savings account, but a certificate usually has what was called a maturity date, meaning there's an amount of time that you have to leave your money in the account. So this says, what is the balance when the certificate matures after 5 years? Like I said, there's usually a date called a maturity date. You have to leave your money in, which is a good thing. Remember what we said, patience is the key with a bank account. So what would the function be? Think about it. See if you can write down the function. Pause the video, try it first. So the beginning amount is $1,000. Remember, with growth, it's always going to be 1 plus the rate inside the parentheses. So 6.5% would be 0.065 raised to the t power, the time. Or you could do 1,000 times 1.065 raised to the x power. Right here, I want to stop for just a second. I want to point out something. Notice that the 1.065 right here, this number, whenever you can look right here and see this number right here, bigger than 1, you're going to know that it's a growth function. Now, there are a few weird examples out there I'm going to show you later on, but for the most part, whenever you look right here, 1 plus the rate, it's going to be bigger than 1. So now we want to figure out how much money is in our savings certificate, what it's worth after 5 years. So we take our function now, we use our calculator to plug in 5 years for the time, or 5 for the x. So we take out the calculator, 1,000, 1.0625 raised to the 5th power, and you get $1,354.08. $1,354.08. So that is how much money I now have in that savings certificate. It is now worth that much money after 5 years. Again, remember, just letting the money sit allowed me to gain this much money. It is important to understand that because a lot of people think they have to work really, really, really hard for that retirement money. And I'm not going to disagree, you need to have a good job. But you can also let your money work for you. All right, so now we're going to take a look at the other side of this. Told you there was exponential growth and there's exponential decay. So although this is going to cause some of our sports fans, including myself, a little bit of sadness, let's talk about March Madness. Or maybe we could call it March Sadness now if we wanted to, right? So when you are looking at March Madness, I know there's slightly different format now because they have a few play-in games, but essentially at the start of March Madness, there are 64 teams. After one game, every one of those teams plays each other, there will be 32 left. After 2 games, there are 16 left, thus the Sweet 16. After 3 games, there is 8 left, the Elite 8. After 4 games, there are 4 teams left, the Final 4. After 5 games, there are 2 left. So this is the national championship game. And then after that 6th game, there's only 1 team remaining. Notice what is happening every single round. Every single round, it is cutting in half. So we took this first amount and we multiplied it by a half. Then we took the first amount multiplied by a half and we multiplied it by another half. Then we took this first amount by a half, and we multiplied it by another half. Hopefully you're starting to get the picture just like we had before. The y value would be the beginning amount multiplied by a half raised to, notice again, there's 3 here, 3 here, 2 here, 2 here, 1 here, 1 here. So it would be raised to the x power. Now there is something I didn't talk about on the last problem I want to point out here. Notice for 0, it would be 64 times 1/2 raised to the 0 power. Well, what is anything to the 0 power? It's just 1 times 64, which is 64. That's why the 0, the beginning amount, always gives you the number that's out in front if you plug in 0 for x. So the same thing applies here. So notice though, this one is decreasing or going down. So let's take a look at what that will look like on the graph. So I'm going to go and I'm going to open a little Desmos page here. We're going to come back to this here in just a moment because I'm going to show you how Desmos can actually be used to help you find the equation for an exponential growth or decay. So we're going to add in a table. So I'm going to go hit that little plus sign right here and hit table. And then I'm going to type in my values for x. 0 after 1 game, after 2, after 3, after 4, after 5, after 6. And then we started off, like I said, with 64 teams. Again, we're excluding the play-in games. 32. And then we have 16, 8, 4, 2, and 1. And I hope now that you look over here, you should be able to see our graph of those points. Notice what it's doing. It's a little hard to see because this one is so spread out. But it starts up here at 64, and then it cuts all the way down. Oh, wow. Come on. Cuts all the way down in half, and then in half, then in half, then in half, then in half, then in half. And it's creating this curve that would eventually flatten out the opposite direction of what this one would. So it would start over here and come down to a flatter area. That's what this is going to look like. Now, in real life, with this example of March Madness, you're not going to go below 1. But if you kept cutting it in half in a graphing situation, what you would notice is that if I kept on going, let's see if we can get this thing to zoom in again. All right, go back and zoom in on those lower points there. If I went back to, oh wow, come on thing. If I went back to my table over here, and I went to 7, and 8, and 9, and I cut that one in half, that would be a 1/2, and then a 1/4, cut it in half, that would be a 1/8, cut it in half. Notice it starts to flatten out. We're going to talk about this when we talk about the graphs in particular, but notice that this would never, ever touch 0. Because you could keep going here. Yes, you could keep getting closer and closer and closer to the axis, cutting in half, but eventually you would still have half of a value. You would never, ever reach in and touch the zero down here, because if you cut something in half, there's still something there. Now, I know that doesn't directly apply to our March Madness example, but that is how exponential decay works. Exponential decay is when you decrease by a percentage. So notice with exponential decay, very similar to what we had with exponential growth, you could have a times b to the x just like we did before, or you could have this c times 1 minus r to the t power. Again, a or c is the initial amount, t or x is the time period, or in the case of the March Madness, the playing games, the round of games that you're looking at. Sorry about that. And then the 1 minus the rate is what we call the decay factor. The r being the decay rate, again as a percentage that you need to change to a decimal before you use it in a real life context. So notice what's happening every time over here. That's a half, Mr. Harrison. That's not a percentage. Well, if you think about it as a decimal, 1/2 is 0.5. So what percentage are you losing every single time? You're losing 50% of the teams every single round. That's the decay rate. That's the percent of decay. So the decay factor would be 1 minus 0.5 or 0.5. Notice that if I have that 1 minus 0.5 or 50%, that is going to always give me an answer inside the parentheses that is below 1. Because it is decreasing, it would be a lower percentage. 50% would be left every single time, every single round. All right, so let's take a look at an exponential decay function. So it says here, from 1982 through 1997, the purchasing power of $1 decreased by about 3.5% per year. Using 1982 as the base for comparison, what was the purchasing power of $1 in 1997? So again, notice this is just like the exponential growth. The difference here being you have the beginning amount and 1 minus the rate raised to the time, or the beginning amount times the decay factor raised to the x power. Like I said, the majority of the time, this 1 minus r is going to be a little bit easier for you to find that decay factor. So, what is the beginning amount? Well, this one's a little tricky to find the beginning amount because you got to realize it's talking about $1 and the purchasing power of $1. So basically what you're assuming here is that in 1982, $1 was worth $1. That's the beginning amount. 1 minus the rate would be 3.5%, so 0.035. Notice again, it's minus the rate instead of plus. Raised to the time. Now that would give me the function again, 1.00. 1 minus 0.035 would be 0.965. Now let's think about what that means. 0.965, that reminds me, hopefully, like I said, that I just subtracted the rate out. So that means it's going to be decay, even if I didn't know it in the first place. Hopefully I do, just because I know I'm decreasing, right? But this also tells me what's happening here. That means every year the dollar was 96.5% of what it used to be. It's only worth a fraction of what it used to be. Just like that example of cutting in half every single time for March Madness. 50% of the teams were left each round. So 96.5% of the dollar is left each round. Sorry, going to get to my problem. So then, if I want to find how much the purchasing power of the dollar actually went down to 1997, I do $1 times that 0.965 raised to the 15th power. So if I do that, if I raise this here to the 15th power, then that means I'm going to take $1 times 0.965 in my calculator. Again, you can use Desmos for this if you need to. $1 times 0.965, and yes, I realize there's an extra zero in there. Just trying to save some time. Raised to the 15th power. 0.586. 0.586. So what does that tell me? Essentially, that tells me that my dollar is worth 58.6% or 58 cents of what it used to be, basically. So in 15 years, the dollar decreased by a pretty large amount. Even though it was only 3.5% per year, notice that it decreases pretty close to 50%. I mean, it's closer to 60% here, but that's a pretty drastic decrease, even though it's only 3.5% per year. Again, that's where it's important to understand the shape of these graphs: exponential growth, making this kind of ramp shape up like this, and exponential decay, making sort of this ramp shape down. Notice that ramp shape is what creates this drastic decrease, and then it kind of slows down as you get closer to zero. The opposite would happen with growth. It's slow at first, but then it increases rapidly as you get farther along, which can be a good thing in the case of a bank account, but a bad thing in the case of the value of a dollar. All right, so let's take a look at another example of exponential decay. This particular example deals with a real-world thing called depreciation. It says you bought a computer for $1,800. The value of the computer will be less each year because of depreciation. The computer depreciates, which means it loses value, at the rate of 29% per year. Now, a majority of us have learned about depreciation when it deals with a car value, and I'm going to talk about that a little bit more in a more live context with a live WebEx with you, because there's more real world and really good life lesson with that one. I want to make sure that we're all together on that one instead of just going through on this video. So, depreciation is when something loses value, like an item, like a computer. A car does the same thing. We're going to first write the function that represents the situation. So we bought a computer for $1,800. That's my beginning amount, $1,800. It loses value 29% per year, so 1 minus 0.29. Again, I will point out here that it's 29% per year. It's not $29 per year, it's 29%. That's how you know it's exponential growth or decay. If it's losing a percentage or gaining a percentage, you're talking about exponential decay or growth, respectively. So what would this equation look like if I actually kind of simplified it down a little bit? And that would be 1,800 times 0.71 to the t, or to the x if you wanted to. So that is 71% of my value is left every year. Or in other words, again, you're losing 29%, but your computer is still worth 71% of what it used to be worth the year before. Now we're going to estimate the value of the computer in 2 years. So if I want to find the value of the computer after 2 years, I do 1,800 times that 0.71 raised to the second power. Or I could do 1 minus 0.29. I do want to show you that that works because I haven't shown you that yet on any of the other examples, but you could do 0.71 raised to the second power, or you could do 1,800, and you can type in your 1 minus 0.29 without actually simplifying it, raised to the second power, and it still gives you $907.38. That is how much my computer is worth after 2 years. So notice that even though I'm only losing 29%, after 2 years, I've already lost 50% basically of the price that I bought the computer for. This is why, even though, new technology is awesome, there's a lot of cool things that it does, it loses value very quickly because of the advances in new technology. So sometimes it's better to wait a little bit longer for that new iPhone because you get more bang for your buck, so to speak. You actually get a much better phone for a much cheaper price if you wait a few years instead of getting one every single year or every 2 years when the new one comes out. So this is an example of when something depreciates by value. So what I want you to do is, before you come see me on WebEx tomorrow or Tuesday, because I'm going to split this lesson up. We are going to do a couple more problems. I'm not done yet in this lesson, so don't give up on me and quit the video yet. I do want you to go through and I want you to take a look at this example. So you may want to pause this and write it down. And then I want you to take a look at this example. You may want to pause this and write it down. And finally, I want you to take a look at this example. You may want to pause this and write it down. So essentially, those problems that I just showed you are going to be our classwork, basically, that I want you to do. And we're going to look at them together on WebEx. It's not your homework. Those are classwork problems. Not to mention the fact that I'm going to give you a little life lesson with this problem on the really nice family member. And I'm going to give you a little life lesson on this buying of a car. So that's going to be something that we use in the live WebEx sessions. Yes, I'll post a video for the live WebEx session as well. The final thing that we're going to do today is we are going to take a look, and actually let me take that back. Let's go ahead and we'll split this up into 2 days. So we'll do 2 things left for today. The final 2 things I want to look at are finding the equation from the graph and finding the graph from the equation. So basically the last thing we're going to finish with is some graphing stuff. If you'll notice, we took this March Madness example and we plugged it into Desmos by making a little table of values here. I am going to go through and I'm going to delete these values so it lines up with the notes that I did just a minute ago, but you could leave those extra points in if you wanted to. It's not a big deal. What I want to show you how to do is I want to show you how to find the equation for these points. So we have the points on the graph, and I want to show you how to find the equation for those points. And so we're going to go over here to our second line. And remember, over here at the top, we have y1 and we have x1. Those are our values. And right here, we did this earlier this year. It's called a regression equation where we find the equation. So I'm going to type in y1, but instead of equal sign, I'm going to hit the little squiggly little sign. It is shift, and it is the little button right beside the number 1. It's this little squiggly equal sign right here, basically. What this is going to do is this is going to give me the approximate equation, or what we call the best fitting equation, or regression equation. But I'm not going to do mx plus b. I'm not going to do ax squared plus bx plus c. I'm not doing a linear. I'm not doing a quadratic. Now I want to write this as a exponential function. So I'm going to use the second way, or the way that our book typically does. I'm going to multiply a times, I'll use parentheses here, b, and then I'm going to raise it to the x power. And I'm going to use my little x1 that's in my little table up there. But the way I do that is I take my little keyboard here, and I use this little raise it to the power. It moves it into the exponent, and I'm going to type in x1. And then that will give me my equation. Notice it gives me 64 for A, 0.5 for B. That is exactly what we found, 64 for A, 0.5 for B. And we found that by hand by knowing the percentage that it is actually decreasing by. You could also do the same thing if it was increasing by a percentage as well for exponential growth. So you can find the equation using the calculator as long as you know how to enter numbers into a table. You add the numbers into the table by hitting the plus sign in hidden table, and then hitting this little y1 squiggly a times b raised to the x1. If you do that every single time, it's going to tell you what a is and what b is. Notice your b value should let you know really quickly if it's an exponential growth or an exponential decay. All right, so we're going to take a look at using that same concept to find our equation for this coronavirus, the one that we've been seeing on the news over and over again. So I'm going to go back to March the 1st. We had 88,585 cases. So we're going to make that 88,585 cases. That's going to be our beginning amount, way up here. Then we're going to look at 1 day later. Actually, I tell you what. Let's go by a week. So let's go to March the 8th. March the 8th would be 109,991. So 109,991. That is March the 8th. Then we're going to go to March the 15th. March the 15th, 169,511. So 169,511. So that, again, notice that is our week 1, week 2. We're going by weeks here. So then after March the 15th, we were going to head up to March the 22nd. That is 7 more days. 337, 459. So 337, 459. And let's do one more. So March the 22nd. Then we went to March the 29th. So let's go to March the 29th. 723, 390. So 723, 390. I'm going to see if I can get those. Yeah, there we go. All right. So now notice my graph has flipped around. And it's going to be hard to see because it's way up in the 80,000 to 723,000 range. But notice that my beginning amount, my A value is here, and my B value is 1.98. Notice what that tells me, 1.98. So let's do 46,412. So this is our coronavirus example here. Our beginning amount, 46,412 right there. Notice that's not the actual beginning amount I started with, but this is a best fitting line. And then 1.98 raised to the x power, because 1.98 would be my b value. Notice what that tells me. Remember, I was doing every week. So what that tells me is that every week I am almost doubling. So it's 1.98. It's almost 2. So I'm almost doubling every single week. And so this would be, the reason that, yes, it's probably a good idea, to watch who you're around and make sure you're not coming into contact with too many people. But this is also, remember, taking into consideration that we have a lot of other things that could be coming into play here. Possibly the fact that we're just testing more people, and maybe it was here a lot longer than we thought. So it may not be doubling every week as much as the fact that it's just we're testing more people. So that's how we use the points and this little Desmos feature. You could also use this stat program underneath the TI-84 and TI-83 calculators and such. Let me pop that up on the screen for you. This is the directions that you would use if you wanted to find the equation of the best fitting line using the TI calculators. That's how you find the equation, and we're going to do that several more times over the next video and maybe some of the WebEx things that we do as well. So the last thing I want to do is I want to talk about what you would do to help you graph one of these things. So now what we're going to look at essentially is what do we do if we want to find the graph of one of these. So I'm going to start with a simple example here, and then we'll move into a little bit more complex example. So let's take a look at the one on the left. So just like a normal function, what we want to do is we want to make a table of values. Notice on this one, we are not given the table. We are given the equation. So what we want to do is we want to plug in some numbers for x. So -2, -1, 0, 1, and 2 would be good ones to plug in. In real life, those values are not good values to plug in all the time. Because if we're talking about time, we definitely don't plug in negatives, right? In this case, we are going to plug in those just because I'm talking about a random graph. So if I multiply 4 times 2 raised to the -2nd power, press enter, it's going to tell me the answer is 1. If I do the same thing, I hit second, enter, but then I type in -1 for my exponent, I get 2. And then I type in 0 for my exponent. Now, let's go back here. I talked about this a minute ago. Remember, 0 would mean you have the beginning amount, which means 2 to the 0 power is 1 times 4. It should be 4. Anytime you plug in 0, you should get the beginning amount 4. So this number right here, kind of like what we do when we're looking at linear equations for the beginning amount, it's my y-intercept. So then the next one, you plug in 1, you would get 8, and then you would get 16. Now, I'm going to assume at this point that you guys know how to graph points. And because most of our stuff is online, you're not going to have to graph a ton of points anyways when it comes to the real test. I'm just going to kind of sketch what this graph would look like. So we are going to count by 2s here. We're going to count by 1s here. Dummy. So my graph would be at -2, 1, -1, 2, 0, 4, 1, 8, and 2, 16 would be way up here. But notice this graph would curve just like we talked about with exponential curve. It has sort of a ramp type of shape to it. And that's kind of what I compare it to. It's sort of like a ramp, like a half pipe or a quarter pipe. Notice though that it's not ever going to come down here and touch 0. When you have this normal exponential graph, it's not going to come down and touch 0. That is a special name. When you have a graph that gets close to a line like that, it gets closer to that line, but it doesn't touch it. We're going to talk about some weirder graphs later on, but this is called an asymptote. I know that's a very weird word, so we're going to talk about that when we meet together on WebEx. So I'm going to ask you guys to be on WebEx a little bit more this week because I want you to make sure that you actually see this a little bit more live. It's called an asymptote when you get closer and closer to a line like that, but you don't touch it. That is called an asymptote. Okay? You can insert your own joke there if you would like. Don't touch the asymptote. So, anyways, that is the basic idea behind graphing an exponential function. Exponential decay would be the same way. It would just be a graph that curves downward like a ramp. I do want to warn you that if you see a negative out in front like this, what that is going to do is that is going to mean your beginning amount is negative, and if you start tripling a negative number like this 3 would do, you would notice a graph that goes down like this. But even though it's going down, that would still be exponential growth. And I know that's weird, but this number in here, remember, is the big key determining factor of whether something is growth or not. The negative 2 out in front tells me my graph basically has been flipped. If you think about it upside down, from a positive 2 down to here, and so it is a negative growth. Think about this. One way to think about that would be the fact that it is an example of like the national debt. The national debt would be growing, but it would be growing this way in a negative direction. So if you made your table of values for this guy, just like we did for the other one, you would notice that right here you would end up with a 0.3, and then you would end up with negative 3 there. Goodness gracious, Mr. Harrison, you're stinking this one up. Let's try it again. 0, negative 2. Then you'd have a negative 6 here, and then you'd have a negative 18 here. So you would see that it's growing in a negative direction. This would be negative 0.67 here, and this one will be negative 0.11, I think, if I remember correctly. So it would be getting lower and lower and lower, but it's growing. Here's the big key. The distance between this and the x-axis is getting farther and farther away. So this distance is growing. Okay? So when we talk about that, we are talking about from here to here, the distance away from the axis is getting farther away. That is a characteristic of growth. Decay can do the same thing. Decay can look like it's actually going up. This guy right here would end up looking like it's going up, but it's called decay because it's getting closer and closer and closer to the axis. And it wouldn't actually be a decay function even though it's getting higher. It would never touch the positive values up here because of this thing that we call the asymptote. The asymptote would be on the x-axis. So the final thing I want to tell you about the graphs of these exponential functions is that they can move around just like what we did when we were talking about all the other graphs this year that move around. Remember how we talked about you can have the opposite of this and the same as this, and it moves it left and right, and it moves it up and down? The same thing can apply to these exponential functions. If you know how to simplify this to just y equals 2 to the x, take negative 2, negative 1, 0, 1, and 2 and plug them in. 2 raised to the negative second power would be 1/4 or 0.25. 2 to the negative first power would be 1/2 or 0.5. 2 to the 0 power would be 1. Notice there's no 1 out in front of this because 1 times this would still be that. That's my beginning amount. 2 to the first power would be 2. 2 to the second power would be 4. If you know how to find those points, those particular points on the graph, let's stretch those out just a bit. Would be here, 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 and here. That's 2 to the x. Let's highlight that so we know what Mr. Harrison's talking about. This equation, though, has a -2 and a plus 3, that means if you take the opposite of this guy and the same as this guy and move every single one of those points right 2 and up 1, 2, 3, right 2, 1, 2, 3, right 2, 1, 2, 3. Notice it's going to be in the same spot there. Right 2, 1, 2, 3, and then right 2, 1, 2, 3. You will get a new graph that has been moved right 2 and up 3, and now the asymptote is now here. Remember we said these lines never cross below the x-axis. So if you move it up 3 spaces, it's going to never cross below 3. Now that would also mean if you moved it down 3 spaces, it would cross below, but it wouldn't go below -3. That is the characteristic of these graphs. So if you can make a table of values for the simple graph, and you can do your opposite same technique, like we've done all year long pretty much, you can get the graph of that function. So, as a final thing on this little video, I know you're looking at it saying an hour long. That's not a little video, Mr. Harrison. Trust me, I know. You can see the time in the bottom right-hand corner that I'm videoing this. When you look at exponential growth and decay, it is things that increase by the same percent over and over, or things that decrease by the same percent over and over. You can find the function by doing the beginning amount, 1 plus the rate for growth, 1 minus the rate for decay, raised to the time, or x if you're using x. You can use this for bank accounts. You can use this for values that are depreciating or going down. You can also use the calculator to help you find that equation, to find that approximation for the regression. And you can also find the graph using our techniques of graphing that we've done all year long by thinking of the basic parent function and moving it left and right and up and down. So that's all we're going to put in this video. In the next video, I'm going to go through a little bit of review of all of this stuff that we did here, a little bit quicker obviously than this video. And then we're going to look at a couple of specific cases of exponential growth and decay. That video will probably come out sometime on Tuesday, more than likely. Your homework will be listed in Schoology, just like it has been all year long. Tomorrow, I will be on WebEx, and I'll be making announcements for times that I will be available. I will try to make multiple times that I'm available on WebEx. I might even try to throw in a late afternoon or a night session if possible, if I have time to do so. So good luck. Don't hesitate to send me questions, but just make sure that you actually watch through the video. Go back and watch it multiple times if you need to. And there's even extra videos on my YouTube channel as well. Love you guys.